expert on black holes, especially how they relate to the galaxies they're in. One of the questions that he's been very interested in is whether smaller galaxies can host previous-sized black holes. Is that accurate?
Yep.
Okay, well then I'll just turn it over to you. Thank you very much.
Okay. I'm actually going to not talk about black holes so much today.
That's fine.
Because this is my third Astro Club talk this fall, and I did black holes as both of the previous ones, so I thought I would
best club,
mix it up a little bit. And since I knew you were excited about Local Group Galaxies, I thought I would focus on Local Group Galaxies.
Thank you.
We are looking right here. This first image is looking through the disk of Andromeda. And this is a background galaxy behind Andromeda. All of the other stars mostly are in Andromeda. That one is in our own Milky Way. So I'm going to give you a quiz to start. So here's an image I took in Escalante Canyon. And everything on this image is in Milky Way, except one thing. What is that?
Andromeda Galaxy.
Yeah, where is it?
Upper center right.
Yeah.
Yeah?
Yeah.
You guys all see Andromeda right there?
Yeah.
You can see the disk of Andromeda? Yep. I have it circled here.
I can see M33 also.
Ooh, nice. Down here?
Up further
There.
right there, yes, above your
Oh,
fingertip.
2 things.
Yeah.
Nice. Good work. Bonus points, for sure. Okay. So Andromeda, I'm going to start talking about Andromeda. I've done a lot of work on the Andromeda Galaxy, and I kind of thought I would tell you a little bit about that. So here is a kind of classic image of Andromeda that was mostly used as is for an Apple desktop at one point. I'm going to show a little movie where we zoom in to Andromeda and look at what the resolving power of the Hubble Space Telescope can show us in this galaxy. And I think the thing about the reason why this kind of gives you an idea of why galaxies in the local group are a really exciting environment to study. And that's because we can resolve individual stars in these galaxies, which we can't really do beyond the local group. So here we're switching to Hubble Space Telescope image, and this kind of noir pattern that you're seeing is actually because we're looking at this carpet of individual resolved stars. And in this image, this is a part of a survey that I was part of about 7 or 8 years ago, where we imaged about a third of the Andromeda Galaxy. And the stars that you're seeing here are all bright stars in Andromeda. So we resolved over 100 million stars in this galaxy.
And that's only in the third of it?
Yeah. But you know that's maybe you know how many stars do you think Andromeda has roughly?
There's a trillion now, half a trillion.
Yeah, something like that. So it's about a factor of 1,000 more than that, or 1,000 to 10,000 more than the number of stars that we saw, right? So we're seeing just the very brightest stars in the galaxy. Stars like the sun would be too faint to see. So all the stars you're seeing in this image are red giant branch stars or young massive stars. The blue ones are young massive stars. All these little orange dots are red giant branch stars.
No red dwarfs, and the red dwarfs are similar percentage in the Andromeda Galaxy that they are in the Milky Way.
Yeah, that's right. So most of the stars, we're seeing only one out of like every 1,000 or 10,000 stars in the galaxy, and these are just the rare bright ones. Just like when you look out and you look at Orion or something like that, and you see you're just seeing these really bright stars that you can see over a large distance. So, I work on kind of how galaxies. I use data like this to look at how galaxies are built up, and the reason I think that's an interesting thing is because galaxies are kind of the building block that connects the initial environment from the Big Bang. All of the stars that we know of in the universe are forming inside galaxies, and then eventually they form planets and life and all that stuff. And so this galaxy formation step is a real key step in understanding the history of our universe. So next image I have here is of the Milky Way. the center of the Milky Way. Anyone know where the center of the Milky Way is on this image?
Right in the middle.
3 degrees east of the Lagoon Nebula.
Okay, just somewhere around here.
Yeah, well, I was going to put up a little higher than that.
Okay. There it is.
Uh-huh.
So you'll notice here that when we look at the center of the Milky Way galaxy, we don't see anything. We see dust. There's dark clouds at visible wavelengths out of every 10 to 12 photons, only one reaches us from the center of our galaxy. That's how much dust is between us and the center of the galaxy.
8% or something.
It's 30 magnitudes of extinction. So stars are 30 magnitudes fainter than they would be in visible wavelengths.
Wow.
So this is why it's useful to study not just our own Milky Way, but other galaxies. It's actually really hard. There's a lot of things about studying our own Milky Way that make it challenging. We don't know the distances to individual objects very easily, although that's changing a little bit with Gaia. And large portions of the galaxy are obscured to us. So that was kind of the motivation for doing this really big Hubble project on the Andromeda galaxy. It was called FAT, the Panchromatic Hubble Andromeda Treasury Program. We had a fancy logo even. This was a really, really big project. One of the biggest projects the Hubble Space Telescope did. It was 828 orbits, so 90-minute orbits of the Hubble Space Telescope. And that translates to about 2 months of time staring at Andromeda. And they did that between 2010 and 2013.
Anil,
Yeah.
is that open shutter time, basically?
Yeah, no, that includes all the overheads.
Okay.
So the 90-minute orbital period includes time when you can't actually look at Andromeda because it's behind the Earth as you're going around, and you end up being able to look for about 60 minutes of that time per orbit. So, and then only about 2/3 of that time is actually spent open shutter. Yeah. And we used, there's a bunch of different cameras on the Hubble Space Telescope. We used two, the advanced camera for surveys and the wide field camera 3. And we used them simultaneously. I'll show you that in just a second. And to get data at 6 different filters from UV, optical, and infrared wavelengths, 2 at each wavelength range. And there was, we detected more than 100 million stars, as I mentioned. And then I'm going to kind of talk a little bit later about this follow-up project on M33, which thank you for pointing out. I'll go back there real quick, which is actually kind of a companion to M31. It's in the same region of the sky as you saw there, and it's actually there's some evidence that they've interacted in the past. And so we had a follow-up project in 2017. Which was a somewhat smaller, but also still pretty significant data project. Okay, so the big deal about the Hubble Space Telescope is that it is a 2.4 meter diameter mirror, similar to what you have out in Tooele. But
but wait.
But it's in space,
And it's not us.
and it's run
Social disaster.
Anyway, yeah. So it's a 2.4 meter diameter in space, and here's an image I like to kind of show to compare what the image quality you get when you take data with the Hubble Space Telescope versus ground-based telescope. This is actually data taken from the Kitt Peak 4 meter telescope. So it's a bigger telescope than the Hubble Space Telescope. And yet when you look at this part of the Andromeda galaxy, what you see is just a blue blob with kind of a red blob up here. And when you look at it with the Hubble Space Telescope, you can see this that this is a very dense cluster of stars, and that these are actually blue and red supergiant stars here that are in that cluster.
There's a lot of bright stars in a little place.
Yeah. Yeah, this is a really impressive cluster. So when we take the way that we took our data here was we took this footprint, this white line here is the full footprint of our survey, and this is the size of one Hubble Space Telescope image. So that gives you a sense of why this, was so expensive in terms of time, telescope time, is that to cover this large area of the galaxy, you need to take a lot of images and mosaic them together.
Can you tell me how many images were involved?
Yeah, 400 and there was 414 distinct points. There's 2 orbits spent on each one. And we actually took data simultaneously. There's 2 cameras in the focal plane of the Hubble Space Telescope. This is the advanced camera Perseverance. This is the wide field camera 3. We took data simultaneously with both of those. And the way that we designed our survey, you can see that there's this kind of block here, was 18 fields where half of them were taken at one orientation. Then we flipped the orientation of the telescope around. 6 months later, we were able to get the other rest of the data. So wherever this camera took data, this camera was taking data, and vice versa. So the whole point of this project was to actually look at these resolved individual stars. So as I mentioned, we have more than 100 million stars. This is a big chunk of the central region of the galaxy here. And what this diagram is showing is a color magnitude diagram. How many of you guys have seen color magnitude diagrams before? Okay, right. So a color magnitude diagram is the same as an HR diagram, yeah. And you plotting in this case, we're plotting a color which is taken by the ratio of the fluxes in 2 different filters. So we get blue stars over here, red stars over here, and then on the y-axis is the brightness of the stars, the apparent magnitude in this case. But because they're all at the same distance, the apparent magnitude translates to relative luminosity. We have bright stars at the top, dim stars at the bottom. But of course, you could also, this color is a proxy for the red or bluer. Bluer, right? So hotter stars are bluer. And then also stars at a fixed size will get brighter as they get bluer. Okay, so
then those are giant and supergiant stars.
Yeah, like I mentioned, so this looks probably pretty different from an HR diagram if you ever saw one before, because our sun is down here, and the main sequence is this goes like this. Okay, all of these stars up here, these are red giant branch stars. Okay, so these are all stars like the sun will become after it's done burning hydrogen into helium in its core. And then this little clump of stars here is actually core helium burning stars in that galaxy. They're called red clump stars or horizontal stars. Yeah.
Did you say this is at the nucleus of the galaxy?
No, this is about halfway out, something like the solar circle.
Okay.
Yeah. And you can see there's this big plume of stars. These are the upper part of the main sequence. These are very hot stars. So the temperatures of these stars are 15,000 degrees or hotter. The mass at the bottom here is something like about 5 solar masses. The stars at the top here are something like 30, 40, 50 solar masses. So these are really the big bright stars that formed very recently in Andromeda. So you can see that here. This is a kind of a simulation of a stellar population as a function of different ages. So you can see it's colored by age. So purple is youngest, red is oldest here. And you can see these youngest stars are on this blue region here. And then starting after about 100 million years, we start getting stars in this red giant branch region. And there's also some young stars up here. These are those red supergiants like that in that cluster we were just seeing. So you can see that we can take boxes in this color magnitude diagram, and we can get different ages of stars. We can dissect the history of this galaxy by using this color magnitude diagram. And that was the main goal of this project, was to understand the history of the Andromeda galaxy. So just based on what I told you so far, which part of this galaxy do you think is the youngest, and which part do you think is the oldest?
Blue is young, yellow is old.
Yeah, and why?
Baby stars are hot and blue, old stars are orange, yellow, and red.
Yeah, so those red giant branch stars, those come from those old populations, and that's what we're seeing at the center of the galaxy is the light, collected light of all of those red giant branch stars. As we get further and further out, you start seeing these dusty areas, and right next to those dusty areas, you see these blue areas where stars have recently formed, and the young, bright, massive stars are still alive, haven't died off yet, and that's why you're getting those nice blue colors. So yeah, exactly. And we're going to get to these guys a little bit later. So if we just take little boxes in the color magnitude diagram and look at where those stars live, we can very clearly see here's the box in the young stellar population area, and you can see that there's very clear rings or spiral arms here. So this is there's a kind of a famous feature in Andromeda called the 10 kiloparsec ring, which is a somewhat off-centered ring, which we think actually may be the result of a galaxy merger in Andromeda. But then if we look at just the old stars, you can see you basically lose all those small scale structures. It's very smooth. And what you see here is the bulge of the galaxy, a bar, and then the extended disk of the galaxy. We've been able to construct the star formation history of Andromeda, and not just the history, but a movie of where stars formed when, or where the stars that formed when live now, is a better way to put it. Yeah. So the part of this work that I worked on the most was identifying and using star clusters to study star formation in this galaxy. So you can see here that there's this nice dense cluster of stars, and these clusters of stars you probably all have looked at through your telescopes, right? There's lots of open clusters and globular clusters in our Milky Way, and those are, probably as you know, those are stars that are all born at the same time. That's what makes them unique. And that simultaneous birth actually allows us to use them as a tool to study where did stars form, how intense was that star formation. And so we tried collecting this sample of star clusters in Andromeda. The problem is that it's actually not very easy to do. So we have 3 billion pixels to look at. I spent about 2 months of my life looking through about a fifth of that. Just going through every image, circling, clicking. We set up a little online program to do this. And then we got about a fifth of the way through the data, and we're like, we do not want to spend 10 months of our lives circling images. We decided to start this project with the Zooniverse people. So I don't know how many people have used Galaxy Zoo before. Are you guys familiar with that? But this is a citizen science project, and we called it the Andromeda Project. And we ended up getting about 10,000 volunteers, maybe some of you. God, I don't know. I actually have met one person randomly who was a geography professor. And I met her, and I told her I was an astronomer. And she said, oh, I got super obsessed with the citizen science project, where you had to circle clusters. I spent like tens of hours on this project. And she turned out to be a volunteer for us. It's the first time that ever happened. So this was very popular. We had had to run for about 25 days to get the data we needed. We had 80 people look at every image and circle where they saw clusters. And we had more than 1.8 million images viewed in 25 days. Here's a world map of all of the people who participated. And there is a kind of over-representation from Utah. So kind of to see what this process looked like, this is a movie made by a former Utah undergrad who's now just finishing his PhD at UC Irvine. What you're seeing here, all the white circles, we had two different tools. One was this is a galaxy. The other one was this is a star cluster. And all the white ones that you're seeing here are star clusters. and all the green circles are things that people identified as galaxies. And you can see that there's a variety of different strategies that people did. There definitely are people who circled many things that were probably not clusters in these images. But we had 80 people looking at every image. So when you see just one person circling something, that's probably not a cluster. But if you see 40 or 50 people circling something, then that ends up being a pretty good cluster candidate.
Our brains like to see clustering and arrangements where none are there.
Yes, that's certainly true. And you know, there's probably some of these clusters that we've identified that are actually just asterisms that are chance superpositions. But I think, you know, the other thing that we did in this process, we inserted fake clusters. So we created synthetic clusters so we could test how well we could see clusters and how well we could do. And so we have a pretty good sense of what we could see and what we couldn't from that. We purposely designed it so that about half of the fake clusters were not detected.
Did you discover any foreground dwarf galaxies at all, or all the green circles background?
They're all background galaxies, yeah. We haven't really one thing I had hoped is that we might discover some clumps of stars, maybe not like just by making cuts on the color magnitude diagram that would allow us to find structures. But apart from the bar of the Andromeda, we haven't really been able to do much.
So what kind of specificity and sensitivity rates were you able to achieve? What was the false positive rate?
So we ended up
just roughly.
Let me explain how we did it, and then I'll get back to that question, because I think I have a little bit of stuff on that. So here's an example image. Here are some that image marked up, and then simplified. This is the fraction of all of the people that identified the object in the image, and you can see that ranges from this thing for about 40% of things to 70 and 80% of people identifying those objects there. And so this is the basic metric that we used, was the fraction of people that identified these objects as clusters. But then what we ended up doing is take that data that I mentioned that we had spent 2 months of our lives. There was 8 of us that identified objects in these green shaded green box regions here. That was the very first data we got down from the Hubble Space Telescope. And we just tested against our expert sample to see how well we did. The completeness that we got was something about like 90% of the objects were in. We had to make a cut at some point of like this fraction of people identifying things as a good cluster, and we found that we got about 90% confirmation with about 10% extra objects that weren't found by us, which we could call contaminants.
Shows the spiral structure quite clearly.
Yeah, so this is actually an ultraviolet image underneath here, and that's why you can see the spiral structure so well.
Excuse me, so the 10% were not actually clusters, is that right?
Well, so then we did an exercise at the end where we looked at, okay, what are the 10% of objects that they didn't find that we identified as clusters, and the 10% of objects that they found that we didn't find, right? So it was similar. And we've actually found that the wisdom of the masses was better than us. There's a lot of ambiguous objects in this. There's always a gray line of what's a cluster and what's not. But we found that, in fact, the things that were identified through the Citizen Science Project were actually better cluster candidates than the ones that they missed. So I think, I would say it's a more robust sample than the one that we identified.
So is there any way to go back and actually confirm at this distance that they're actually clusters, that they're gravitationally bound? Is there some physical
it's
physics
pretty
method
hard
to do
for
that?
most of them because they're so low mass that you can't. I mean, the way to do it would be to get velocities of the individual stars and confirm that they're at the same radial velocity and that their velocity dispersion is low, like a couple kilometers per second. That is a very challenging measurement to make. In fact, like we're pretty sure that almost because we can make synthetic clusters that are like bound objects, and we can look at what those look like. We're pretty sure that a vast majority of the objects that we've identified are in fact bound clusters. This is the final cluster catalog and galaxy catalog, both. The circles are actually sized by the size, proportional to the size of the clusters that we identified. And you can see there's kind of some interesting, you can very clearly see the spiral arms amongst the clusters. And that's because most of the clusters that we're identifying are open clusters that are young collections of young stars. Those clusters dissolve over time, and so away from the spiral arms, you tend to see fewer clusters. They also get fainter, and so they're harder to identify as they get older. Yeah.
With our galaxy, don't the clusters orbit, the globulars orbit outside the galaxy?
Yeah.
So they wouldn't be in our spiral arms necessarily.
Well, but there would be some, we would expect, I mean, there were about 35 globular clusters previously known in Andromeda. So most of the globular clusters in Andromeda were previously known because they're really bright, and that are projected in our area. Maybe there's even more than that, maybe 50-ish. And we identified those as well, but most of those were already known.
So these are all open clusters.
So a vast majority of them are open clusters. So the total sample was 2,700 clusters, and this actually is the largest sample of any of clusters that are kind of uniformly selected in any galaxy, including our own Milky Way.
That's far out.
Yeah. And there was only, in the same region, there was 466 previously known clusters. Again, most of which were open clusters, but something like 50 or so of which were globulars. And you can see here, this is the magnitude. So faint things here, bright things here. You can see that almost all the very bright objects were known. But as you get to fainter objects, we detected many, many more faint clusters than previously.
I like that very bright is 15th magnitude.
Yes. A globular cluster, a typical globular, that's a bright globular cluster in Andromeda. Right? So Omega Cen in Andromeda would be at 15th magnitude. So
I've hunted a few of those with a 20-inch.
Okay, so we have this big giant sample of clusters, and then the question is, what can we do with all this? What's interesting? And the thing that, because these are mostly young clusters, the thing that we've been working primarily on is studying how stars form. These clusters are kind of giving us signposts of the most intense epochs of recent star formation in Andromeda. And I think the most interesting, I'm just going to talk about kind of the most interesting result that I think we found from this. And this is just looking at the mass spectrum of clusters. These are all young clusters. The mass spectrum of young clusters in this galaxy. And what's showing here is the number of clusters per unit log mass. And then this is the mass, and it's the logarithmic mass, so this is a 10 to the 4 solar masses. So this is like 10,000 solar masses, 1,000 solar masses, this would be 100,000 solar masses on the right-hand side. So you can see that there's a lot of really low mass clusters, and then that declines very precipitously as you get to higher masses. And what the interesting thing here is that if you can fit this with a power law index of, so you can basically just extrapolate, and you expect that there'd be a whole bunch of massive clusters that we don't see. And we actually see in the Milky Way and many other galaxies that a power law is pretty good for describing the mass spectrum of clusters and the mass spectrum of giant molecular clouds. And so we think that there's some process here which is preventing the most massive clusters from being formed. Something like gas.
Yeah. Is there any possibility that they form but they dissipate really quickly?
No. So the most massive clusters should be the most robust ones.
Yeah, right.
So they should be able to live the longest. And so if they formed, we would see them. And they're also the easiest to detect. So we really are pretty sure that they're missing.
What are the lighter lines supposed to represent?
So these are data. These are fits, and they're model fits to the data, and each one is 100 fits. So it's they're kind of sampled from the distribution. We're not actually fitting this histogram. We're fitting the mass spectrum of the individual cluster masses.
Could metallicity have anything to do with that, like maximum star mass?
Well, so what we think is actually really happening is that it turns out that Andromeda is a really wussy star-forming galaxy. So it's a spiral galaxy. It's got gas. It's turning gas into stars, but it's not doing it very rapidly. So you probably know some of these galaxies, M51, M83. They are forming stars. This is the star formation rate density. So how per unit area in the galaxy, how many stars are being formed. What you can see is that they're more than an order of magnitude more rapid in their star formation. So they're cooking out stars really well. This thing up here, the antennae, I don't know if you guys are familiar with that one, but it's a famous interacting galaxy, and it's forming this huge number of stars. And what's plotted on this y-axis here is where this starts to bend. Okay, so that's what this MC parameter, this the maximum cluster mass is what we call it. And you can see that maximum cluster mass seems to depend pretty close to linearly on this star formation rate density.
Now, M51 and the antenna obviously are interacting galaxies.
Yeah.
Does that have anything to do with it?
Yeah, so that's part of the reason they have enhanced star formation rates. When galaxies interact, the gas tends to get shocked and forms extra stars.
So where's the Milky Way on the right-hand diagram?
So the Milky Way would be somewhere in between these two galaxies, actually. Yeah.
Yeah, know where M82 would be?
M82 would be in this same region.
Probably, yeah, right.
Yeah, on this axis. You can see that we only have 4 galaxies on this diagram, and part of the reason is this measurement is really hard to make. So, we took this 2,700 clusters, you bin them up, and this is what we get, right? And you need really that large sample and a large dynamic range of masses in order to be able to make the measurement. And so we don't have the data in many other galaxies to make this measurement. But the kind of exciting thing about it is that you can actually measure the same downturn in the mass spectrum of globular clusters. And we know that that mass spectrum varies. So in the most massive galaxies, the globular clusters are populated to hide the higher masses. In less massive galaxies like the Milky Way, this turnover happens something like here. And so we can connect, if we assume that the globular clusters were formed in a similar environment to the clusters that are forming today, we can actually kind of infer, based on the globular cluster population of a galaxy, what was its star formation rate density when those globular clusters were formed. So we can use the globular clusters to kind of do some archaeology on the galaxy histories from this relationship. And so that's actually the reason why I find this really exciting, is it allows us to kind of use these clusters as a tool to study the history of the galaxies.
I'm sorry, could you explain that again?
Yeah, so you can measure the mass spectrum just like you can do for the young clusters. For globular clusters, it's actually more of a Gaussian shape, or because the lowest mass clusters all get dissolved away. But you can still measure where this downturn happens at the high mass end. And so and there's kind of a leap here, which is that you assume that globular clusters formed in the same way that we're seeing clusters form in today's universe. And if we do that, then we can infer the star formation rate density that those globular clusters must have formed based on the mass spectrum of those clusters. So that's the kind of an exciting result from this. Okay, so now I'm going to kind of, for the last little bit, I'm going to talk about other galaxies in the local group. You probably are more aware of this than me, since you. But if you go out at this time of year, the many galaxies of the local group are visible, especially the galaxies that surround Andromeda. So there's the 2 galaxies that you could see in that previous image, NGC 205 and M32. There's M33 here. There's other companions of Andromeda, NGC 185 and 147, which are dwarf galaxies. And then there's a number of other dwarf galaxies here, Fornax, W11, I66, and 13. So there's this all of these galaxies that are shown in green here are part of our local group, meaning they're gravitationally bound to the Milky Way and Andromeda. And this is a pretty unique environment for studying galaxies, because this is our backyard where we can see all of the little tiny fluffy galaxies. We can see the whole mass spectrum of galaxies, and we can study in detail what does their history look like. And so the main thing that we kind of determines what a galaxy is like is its mass. Right? So just it's also true for stars, right? a star's mass determines essentially what it's going to happen during its lifetime. And similarly for galaxies, the mass in stars is a good way of kind of understanding or grouping together galaxies. And what this is showing is just the number of galaxies that exist in the universe as a function of stellar mass. And you can see that there's this, just like that, the bend in the cluster mass function, there's a bend in the galaxy mass function here. And the Milky Way and M31 are sitting right at where that bend is. Okay, and that's not a coincidence that we live in a galaxy like that. Something like half the stars in the universe are in galaxies that are within a factor of 10 of the Milky Way mass. Okay, so the typical galaxy, the typical star in the universe lives in the Milky Way galaxy.
That's far out too.
But that does not mean the typical galaxy in the universe is a Milky Way galaxy, because there are way more low mass galaxies than there are. So you can see here, this is a logarithmic scale. Down here, if we look at galaxies like Sextus A or Fornax here, there are dozens of those galaxies for every Milky Way galaxy in our universe. And you can see that just from this image here. There's one big galaxy, M31, and there's this whole constellation of galaxies around it that are lower mass. Okay, and so this is really what we've learned from the local group, is actually what this spectrum of different galaxy masses looks like. These galaxies down here, we can't detect outside the local group. These lowest mass galaxies, the only place we can find them is in the local group. So here is a compilation from, it's now like 7 years old, so there's definitely some galaxies missing, but a compilation of local group galaxies. And red here, this is in galactic coordinates. Okay, so the plane of our galaxy runs right down the middle here. So the fact that there's not a lot of galaxies right down the middle here is related to exactly the same problem that I was showing earlier. We can't really see through the plane of our galaxy very well. But you can see the red upper part is actually satellites of the Milky Way. These are galaxies that are within a few hundred, about 1,000 light years of the Milky Way. Sorry, 10,000 within. Sorry, they're within 300 kiloparsecs, which is 1 million light years of the Milky Way. Yeah. So these are all the bound satellites of the Milky Way. They're orbiting directly in the Milky Way. And they're galaxies that some of you may have heard of, so Carina, the LMC and SMC, you've certainly heard of probably. These are the biggest satellites of the Milky Way. Fornax, Sculptor. And when we look at, and then down here, these galaxies are, you can see there's this big clump of galaxies around M31. And then there's these green objects are objects that may or are probably not bound to either Andromeda or M31, but are kind of orbiting in the joint potential of both galaxies. Okay, so there's this whole sea of galaxies in the local group, and we've learned a lot from these galaxies about how galaxies of different masses look. So I'm going to start just kind of stepping down in mass from M31, which is probably the heaviest galaxy in our local group, pretty similar to the Milky Way. If we go down by a factor of about 50 in mass, there's two galaxies in the local group. One is the Large Magellanic Cloud. This is an image that's not actually an image. It's created from data from the Gaia satellite, and try to infer what's the number of stars in the LMC here. So this is a kind of a number counts image of the Large Magellanic Cloud. And then this here is that other project I referred to, Hubble Space Telescope imaging of the galaxy M33. And that galaxy, just like Andromeda, is chock full of stars and star clusters. We've been working on trying to create a cluster catalog. Here's our initial cluster catalog for data in M33. We threw in some old data that was taken previously, as well as our nice big contiguous block that we have near the center of the galaxy. And this is actually work that I'm doing with a couple undergrads here, Stephanie Torres Villanueva and Tobin Weiner. and my old student Cliff, who's now at Northwestern University. We're working on getting out the first publication of the cluster catalog right now. And hopefully we'll be able to make measurements kind of similar to the ones, cluster has like about 2,000 clusters, and we'll be able to make measurements similar to the ones we made in Andromeda.
Definitely shows they're clustered in the spiral arms.
Yeah, so this is again an ultraviolet image that underneath here, and you can see that the clusters are accompanying the bright young regions, again, just like they were in Andromeda. Yeah.
Is there any attempt to parse out which are globulars and which are open clusters?
So we're in this. It's turned out that in this citizen science project that we did here, there has been we didn't do a very good job of training people to look for globular clusters. So the globular clusters are mostly identified as galaxies in our by our volunteers, but it's fairly straightforward for us to do because the globular clusters cut off at the low brightness, so they're really quite different looking in our images than so we kind of we're separating them out by hand, I guess.
So I gather the globs wouldn't necessarily go along with the spiral arms?
No, and there's many fewer in M33 than there are in Andromeda. I think there's only 5 or 6 in this footprint.
Globulars are distributed in spherical orbits around the galaxy.
Yeah.
Only open clusters are in the plane.
They are concentrated, like in the Milky Way, the globular clusters are concentrated towards the center of the galaxy too. So the ones that we're most familiar with are the ones that trace the halo of the galaxy. But there are a population of metal-rich globular clusters that are essentially tracking the bulge in the thick disk of our galaxy. Yeah. So here's 2 more dwarfs that are of a similar mass to M33 and the LMC. But they're different. These galaxies are pretty much lacking in gas. So they're not forming stars anymore, like the Large Magellanic Cloud and Andromeda. And this is one NGC 205. This is the other one, M32. And you can see here they're pretty different looking. Okay, so M32 is extremely bright. If you don't know, I don't know if you know this, but it's the brightest place in the universe. So if you're looking with an optical telescope from the ground, the highest surface brightness place in the universe is the center of M32.
That's far out too. I looked at M32 a lot and never knew that.
Yeah, so if you want to take a really nice spectrum of a galaxy, the M32 is the best place to do that. And so M32 is this really dense ball of stars. It's way smaller than NGC 205, and you can see that in this image, right? It's much smaller, but they're about the same mass, so it's just way more compact and dense. NGC 205 is what we think of as kind of a typical lower mass galaxy.
There's structure visible in M110 or 205.
Yeah.
In that image and in a good visual.
Yeah, you can see this kind of S shape.
And all the little like dust lanes, tiny bits of dust.
Yeah, there's some dust lanes too. So there is a little bit of gas in NGC 205. There's actually some recent star formation near the center.
You see that in a 12-inch on a dark night.
Nice. Yeah, I've looked at it from Frisco, and it's definitely yeah. As is you can see you can't really see it. There's a star cluster sitting right at the center of. I have a nicer image in just a second. So first, I was going to talk about M32. So M32, we think actually might be. There's been recent work on whether M32 is actually the core of a galaxy that has been torn apart by Andromeda. So the idea here is that it would be something that would be maybe 1/5 the stellar mass of Andromeda, and it fell into Andromeda something like 2-3 gigayears ago. There's some circumstantial evidence for this, and what's shown here is actually a simulation which is showing where stars would go based on an orbit that would end up sticking the core of M32 in the right place and creating the giant stellar stream that we see in the halo of the Andromeda galaxy. And so this is a kind of I would say, a somewhat controversial topic. There's some people who think M32 is a compact, very bright galaxy because it was formed from some sort of merger and of two small gas-rich galaxies, and it's just a unique kind of galaxy, very rare in the universe. And other people think it's just the central part of the galaxy, close to the mass of the Milky Way, where all the outer parts have been pulled away. And so that's kind of an ongoing debate. Here's a nice picture of NGC 205, which as you noted, was also M110. You can see these little dust lanes here. You can see the nuclear star cluster of this galaxy. And this is actually a galaxy I've been working on recently with a graduate student of mine, Yoon Nguyen. We think this galaxy might host the lowest mass black hole that's at the center of any galaxy that we know. And so it's a pretty subtle measurement. So I would say we're not very sure of it. This is a map of the motions of the stars at the center of the galaxy. You can see the stars actually move slower near the center than they do further out. That's the opposite of what we'd expect from a black hole. But we can very carefully measure the mass distribution of stars, and we can find out that the stars actually are moving faster at the center than we would expect them to. And we think that might be due to a black hole that's about 10,000 times the mass of the sun. And that's about 2 orders of magnitude lower than the one in the Milky Way, and the lowest mass central black hole that has been measured. The challenge of this measurement is that we're trying to measure something we don't see, right? We're trying to infer it kind of indirectly, and there's other things that could mimic that signature. And so one of the things that we're worried about is that, for instance, individual stellar mass black holes could collect as a clump near the center of the galaxy, and there might be about 10,000 solar masses of those, and that would look exactly the same to our measurements.
I thought I read that there should be some kind of microwave signature of that. Am I incorrect?
So if there's a single black hole, that would be likely have the most that would be the most likely to emit wavelength radio emission and X-ray emission. We actually have a proposal right now with the Chandra X-ray Observatory and the VLA, which will execute simultaneously to try getting very deep images to see if we can find that source. If it was a collection of stellar mass black holes, we wouldn't actually see. We'd be less likely to see that.
The high energy production.
Yeah.
And if there were clusters of stellar mass black holes, how long would a cluster like that be able to live in a galactic center? Yeah.
So this galactic center is actually a lot like a globular cluster. It's about 1 million solar masses, so it's like a big globular cluster. There's a lot of recent evidence that there are stellar mass black holes near the centers of galactic globular clusters. We think that maybe the LIGO sources, the merging black holes that people have been detecting, are actually in globular clusters. It's a little bit of an issue in debate, I would say, about what fraction of the black holes in a galaxy or that are formed in a cluster are retained in that cluster. And the reason why it's hard for us to know is because when a supernova blows up, it can provide a kick to the remnant. So, like, if you know that supernova blows up, you get a neutron star or a black hole left behind. That neutron star and black hole doesn't typically just sit there. It's often the supernova will kind of blow up more preferentially in one direction, and the remnant will go the other direction. Okay, and the problem is that we don't have good measurements of what the velocity spectrum is. And if those kicks are pretty high, then they'll just get kicked right out of the cluster, and most of them won't stay in the cluster. If those kicks are low, then they can be retained more easily. And then there's this whole dynamical interactions that will happen. They'll gradually settle to the center and form this kind of cluster that can be fairly long-lived. Yeah.
Do you recall any estimate for a mass of the black holes maybe in M15?
Yeah, so M15 I'm almost sure doesn't have a black hole, individual black hole in it. It probably has a collection of stellar mass black holes at the center of it. there, the mass inferred is something quite similar to this. It's like a few thousand solar masses. So,
Okay, that's, I like that.
so yeah, this could be an object more like M15, and then this wouldn't be a central black hole.
So do you expect to get any results anytime soon?
Yeah, so I mean, we're supposed to, the data, because we're getting it simultaneously, it's taking longer for us to get, but it's supposed to be taken sometime during 2020.
Then you'll have an answer, is that right?
We'll have an answer if we detect something. We won't know for sure if we don't. Yeah, it's kind of a one-sided answer. So as we go to lower mass galaxies, things are like 100 million stars, 10 million stars, 1 million stars. We call these things dwarf galaxies. Here's two different types of dwarfs. There's kind of dwarfs with gas, just like we saw in the more massive galaxies. Dwarfs with gas, well, dwarf irregulars. And there's these galaxies called dwarf spheroidals. This one is the Fornax dwarf spheroidal here. Which actually has some globular clusters. You can see there's there's actually 5 globular clusters.
Another 12-inch telescope target.
Yeah.
What does SF mean? What does SF mean?
No star formation, sorry. Yeah.
So do these have low mass black holes at their centers? Or?
We have no idea at this mass range. So we know that above about 1 billion solar masses, black holes are pretty common. At this mass range, we don't have any measurements. So in this galaxy, this is NGC 6822. It's a beautiful local group galaxy. You can see these really nice H-alpha star-forming regions, bubbles being blown. So this galaxy is actually embedded in this huge disk of neutral hydrogen gas. So this is observed in the radio part of the spectrum, this neutral hydrogen gas, and you can see that the stars are just occupying the central region here. There's actually a little bit of a hole in this gas. We think that was actually blown by a star formation event recently. The mass in gas actually outstrips the mass in stars. There's more gas mass in our stars, and that's pretty typical of galaxies like this. So here's kind of a census of these dwarf galaxies. In the local group here, so this is the green line here, you can see here this is the luminosity of those, and roughly speaking, the luminosity and mass is pretty similar. So things that are about 10 to the 8 solar luminosities are about 100 million stars. And you can see that there's many of these. There's like 20 galaxies in the local group that are about 1 million solar masses or less. And these things are really only these objects are only found in the local group. The very faintest objects are only found in the Milky Way.
And that's just because of our observation, right?
Yeah, and that's just because we can't see. They're so faint, so low surface brightness that we can't see them around other galaxies. So one of the things that we found from looking at the local group and other nearby galaxies is that generally the galaxies that are closest to the big galaxies are the ones that lack the gas. Okay, so what this plot is plotting here is the distance to the closest big galaxy, either the Milky Way or M31 for local group galaxies. And then this is the ratio of the gas mass to the solar luminosity, the luminosity in stars. So objects that are up here are gas rich. Objects that are here, all these arrows, are gas poor. They don't have any gas in them. And what you can see is that there's this dashed line. All of the objects that are gas poor, almost all, except for a couple, are they're orbiting the Milky Way or Andromeda. So these dwarf spheroidal galaxies, as we call them, these gas poor dwarf galaxies, those are being caused by somehow that loss of gas is related to the fact that they're living around another big galaxy. And we call that process quenching, and it's a really active part trying to understand why those galaxies are quenched. It's a really active field of research in astronomy. One of the questions that these small galaxies have prompted is, do these galaxies have dark matter halos? So are they surrounded by dark matter like we see in the Milky Way and other big galaxies? And this is a plot of the luminosity of an object versus its size. So you can see these black dots here. These are globular clusters. They're pretty bright, but they're compact. You can see at the same luminosity, there are objects that are much, much bigger, a factor of 10 or 100 bigger. Those are these dwarf, very low luminosity dwarf galaxies, ultra faint dwarf galaxies. And we see a lot of them around the Milky Way and Andromeda. And if we measure the motions of the stars in those galaxies, we can infer the mass. And what we found is that as you get to lower and lower luminosities, that you find more and more mass relative to the amount of stars that are there. So, this is what's called the mass to light ratio, meaning what's the mass inferred due to the motions of stars relative to the luminosity of stars. And as you get to the lowest luminosity galaxies, you see that that's about a factor of 1,000. So these objects are extremely dark matter dominated.
Dark matter rich, yeah.
Yeah, so they have a few stars, but they're sitting in big dark matter halos. And so that's one of the things we've learned from the local group.
Where's the Milky Way in there? Or can we figure that out?
So the Milky Way would be up here, and it would be out here. It would be within the half light radius, and basically there's almost no detectable dark matter within the half light radius of the Milky Way. It's dominated by the stars.
So could there be dwarf spheroidal galaxies that were virtually all dark matter?
Yeah.
And we could detect them perhaps by what they do to background objects,
Yeah.
lensing or something?
Yeah, so that is totally something that people are trying to do. There's been papers written about that just recently. We talked a couple weeks about a paper about that. So there's all these galaxies. There are dark matter halos, and there's a few stars in them. One of the expectations from galaxy formation models is that there should be galaxies that have no stars in them. Dark matter halos that have no stars in them. What people are trying to do is, so I'll go to the next slide actually. So if we look around galaxies, we can see these streams of stars in the outer parts of, so this is the outer part of Andromeda and N33 here. You can see that there's these kind of streams of stars like here and here, and we've been detecting, and here, we've been detecting these streams in our own Milky Way as well. And one of the expectations is that if a dark matter halo goes through those streams, they'll open a little gap in the stream gravitationally. And so the people have been really actively looking for that now. Okay, so
is there any observational evidence that dark matter has any composition of machos, of massive objects?
We do not know yet that at all. Yeah. So the nature of dark matter isn't all constrained by any of the astrophysical observations.
We had a U of U professor speak to us back in 2009. She told us this particle physicist. She said, "We will know dark matter's place on the particle."
Probably
tube.
Pearl.
Yes, Pearl.
But it could have been 2009 because she wasn't here until 2011. We both arrived the same year.
2011. Those years blur, but she said in 2 years we'll know where it goes on the particle zoo. We'll know everything there is to know about it in 2 years.
She's more pessimistic now.
Yeah, I guess so. Jugs.
Okay, I just was going to say a couple last words on kind of like what's exciting right now in this kind of field of studying nearby the local group and local group galaxies. And one of the most exciting things is the data from the Gaia satellite. So you probably know that Gaia is measuring the positions very accurately of many stars and does that repeatedly, and that allows you to get parallaxes as well as proper motions of stars. And parallaxes allow us to measure distances, geometric distances. And one of the things that Gaia has revealed is that there is stars on orbits that are kind of grouped together, and it represents a really large fraction of the stars in the halo of our galaxy. And this people have realized that this must come from a single galaxy that merged with the Milky Way, and that they dubbed it Gaia Enceladus, or the Gaia sausage. And so that's been discovered in the last 2 years, that there's this very clear structure of stars, and In fact, there's also these big numbers here are 13 globular clusters, which are likely associated with that galaxy. So they were formed in that galaxy. The galaxy merged, and those globular clusters and the stars got mixed around in our galaxy. But we can see the signature of those in the orbits that we can determine.
I'm sorry, where's the sausage?
So it's all around us. So so there's these stars all around us, but they're on orbital. The reason it's called a sausage is actually on diagrams of the velocities of stars. It makes a little kind of sausage-like shape on that.
So where's the sausage on that image?
So these stars are all stars that we think are in the sausage, and they're colored by their parallax. So you can kind of see there's a structure here that's cutting across. So because this galaxy merged a long time ago, the stars are mixed around our galaxy really well.
So is that structure have the same position as the giant stream that DSS, the Digital Sky Survey, found a few years ago? There's a big streamer that goes
so there's a big stream that's coming from the Sagittarius galaxy. It's an ongoing merger. This is a much older merger and probably from a much more massive galaxy. So Sagittarius is something like a few times 10 to the 8 solar masses. This thing was probably order of magnitude larger than that.
So the yellow stars are most nearby, or the yellow dots. But the stars themselves are objects that were not formed with the Milky Way.
Yeah, that's right. That are coming in from outside the Milky Way. That's right.
The areas that are blocking that too is dark energy and dark matter. Is that correct? Or
so in this case, this is the plane of the Milky Way here. That's kind of cutting across there that we just aren't seeing the stars. And then this is just areas where there aren't as many stars. Nearby. So one of the kind of things that I'm really excited about is it turns out that you saw that NGC 205, for instance, has a dense star cluster at its center, about 1 million times the mass of the sun. We have a big cluster in our Milky Way. It's called Omega Centauri. It's the biggest one. It's about 2.5 million times the mass of the sun. And there's a lot of evidence that it was the center of the galaxy, the Gaia Enceladus or Gaia Sausage galaxy. And there's that evidence is being put together kind of just right now. I just submitted a proposal this year to try getting spectroscopic data of the central region of this object to get it to understand its formation history. So the last thing before I finish is that people are really intrigued by enigmatic finding, I guess, which is that around both M31 and the Milky Way, it looks like the satellites are in a somewhat thick, rotating plane of satellites. You can see here that there's this red line here that's a great circle, and many of the satellites, their Andromeda satellites, are lying along it. And this is actually data from the Gaia satellite, which shows the motions of galaxies. You can see that there's this kind of circular pattern here, and this is looking at it. So because we have both the positions and the velocities of the galaxies in 3 dimensions, you can actually make a map of what it should look like. So this is the edge-on view of that plane of satellites. This is the face-on view of that plane of satellites.
There are some galaxies that have real distinctive rings. Would that be related to this?
Probably not. So we don't really understand what's going on here. So this is why I'm putting it up here. There's a lot of controversy about whether this is how unexpected this is. So the people who found these things went into simulations of galaxy formation and said, these structures don't exist in those simulations. This is crazy. This is telling us that we don't understand how our universe works.
So could it be fossil evidence of a pre-galactic nebula, a pre-local group hydrogen cloud?
So these are all individual galaxies that have dark matter halos. Okay, so it has to be something a little bit different than that. It could be evidence for some sort of group of galaxies that merged with the Milky Way and along a preferred direction. But you don't expect this sort of structure to be around. It would have to be an unusual structure if it's, like the Milky Way would be rare. relative based on the simulations of galaxy formation. So this is kind of an ongoing challenge to simulations of galaxy formation and dark matter, our dark matter paradigm of the universe. And so that's an exciting thing that maybe 5 years from now I'll be able to tell you how the results.
We'll look you up.
And I'm closing with this, which is I just found out today is going to be a Hubble Picture of the Week from a galaxy that I took data from with the Hubble Space Telescope a couple years ago. It was team number 2. Okay, thanks.
Thank you.
Thank you.
That's a really eccentric galaxy.
Yeah. It's funny because this image is way better than any of the ones I made myself. And it is a very odd-looking galaxy. Looks like it has a big loop around the outside of it.
Well, we want to thank you very, very fervently for this wonderful lecture that I'm going to be chewing over for a long time.
He's really the best.
It's really
He's a good
great.
teacher.
Thank you very much.
Thanks.